We begin chapter 6, and as usual, I am pushing doing the homework problems. I can't tell you the number of students who say they've put in a ton of time and just don't do well on the exam. And when we really sit down and talk, they say, well, I sort of really didn't do the homework problems. And to be honest, this is a college level course. It's a science course. You really do need to do the homework problems. So this is called Chapter 6, The Electronic Structure of Atoms. And as I have taught it, I think I have added more listening to what students have asked me. When we have any sort of chemistry going on, it really depends on the electron. So this chapter really focuses on it. And we've already done redox, where we looked at oxidation and reduction reactions. So what you've had so far really is what's called classical mechanics. You've heard about Dalton with the postulates that he made about the atom. You heard about Thomson, who did the charge to mass ratio. You've heard about Millikan, who worked on the Coulombic charge, and then Rutherford, who did alpha, beta, and gamma particles, as well as what is the nucleus and protons, followed by his student, who then did neutrons. That's all what we call 19th century. Matter is made of particles, light is made of waves. What we're going to do now is bring you into quantum mechanics, and that's what this chapter is all about. Planck, Einstein, Bohr, Heisenberg, and Schrodinger. And what it did is it gave that word insight. It let people see how matter, light, waves, and particles are related. And if you've never heard this before, it really is pretty amazing. So the tool that people primarily use is spectroscopy, which looks at how is radiation absorbed and emitted. So what is the absorption of energy? Well, matter can capture electromagnetic radiation, and it converts the energy of photons to internal energy. Internal energy was a topic of chapter 5. When something absorbs, what you get is a spectrum, and you see 3 of them below. Some are useful. Chlorophyll, that's how we have energy in plants. Some of them can be harmful, and that would be UV radiation, which can give you a sunburn, eventually to cancer. Your human retina has rods and cones that absorb at different parts of the absorption spectrum. And then there's looking at the spectrum of carbon dioxide, which lets people understand what goes on in the atmosphere. So all of these things are called spectra, and substances have what we call fingerprints, and you can see the 3 examples below. Now, if we talk about the other word, emission, what does the emission of energy mean? Well, when we have an electron that is excited to a higher energy level, we're going to explain that, what it will do is decay to a lower level. So possibly you've watched Breaking Bad, and you've seen them do some of the things that are done here. We have a demo I hope to be able to work into lecture. Let's say you have a glow stick. That is luminol, and that could also be fireflies. So you have seen examples of emission. Okay, so that's the visible things we can see. What we're going to do in this chapter is talk about light and mass and particles and waves. So first we talk about the wave nature of light. And we describe it in 2 different ways. We describe light either with a wavelength, and that is the Greek letter lambda. And it is the distance between consecutive peaks of a wave. Down here I have the ocean, here we have some waves, but really a wavelength to a scientist is what is the distance between 2 consecutive peaks. Frequency, that's the Greek letter nu, that's the number of peaks that are going to pass through a given point in a second. So 2 new terms if you're not used to them before. The proof that this happens are the interference patterns, and here you can see some made by a boat on a lake. The relationship, what was observed is frequency is inversely proportional to wavelength. So what they did is they replaced the proportionality with a constant and an equal sign. And the equal sign and C, that is the speed of light. So here is the electromagnetic spectrum, and there are many, many forms of electromagnetic radiation, and they differ only by, shall I say, frequency or wavelength or energy. I'm going to put some less than signs here. I'm going to say X-rays have a smaller wavelength than visible light. Visible light has a smaller wavelength than heat. Heat has a smaller wavelength than microwaves, and microwaves have a smaller wavelength than radio. Know the order. You can memorize them in terms of the wavelength, or I'd say the energy. Energy is developed in the next section. So here is the picture from your textbook. You'll see that what we have written above corresponds to it. Here, I put this in here also from your textbook. All the different symbols, all the different metric units that are described to that are used to describe radiation. When we look at, well, visible, notice that we're talking about nanometers. I think that kind of surprised me. I don't know why. And the other one that surprises me is TV and radio when you go over the air. That's in terms of meters. But that is not what our course is about. Our course is about chemistry. Okay? The last slide in this section says we want to make sure you know how to convert between wavelength and frequency. There are really two ways to do this calculation. I'm going to show both. It says wavelength is the speed of light divided by the frequency. The speed of light is 3 times 10 to the 8th meters per second. The frequency given is 5.64 times 10 to the 14th per second. That's also what seconds minus 1 means. Numerically, 5.31 times 10 to the minus 7 meters. Notice it wants it in nanometers. So you would have to add in the fact that there are 10 to the 9th nanometers for every meter, and that tells us that we have 531 nanometers. If I look at a chart, that is green. Students just exploded when they said, we don't have to know the names. I said, no, you really just have to know the wavelength. But let's apply what we learned in dimensional analysis, okay? If we have 3 times 10 to the 8th meters per second, and then we say for the frequency, a second is 5.64 times 10 to the 14th. It's really the frequency, it's the cycles. And then let's do the calculation all at once. A meter is 10 to the 9th nanometer. That gives us immediately 531 nanometers. Why am I pushing this? Well, you've got a year of Gen Chem behind you, ahead of you, not behind you. And you're going to have to do a lot of calculations. Yes, concepts are important, methods are important, facts are important, but so are the calculations, because as you look at how things are organized, it will give you the insight. And again, that is the main reason you're taking this course. So once again, I always say, questions, please ask them.